In this video, we'll talk about another approach to the area between two curves or areas of regions in the plane problem, where we now look at things in terms of y versus x to look at regions that are easier to look at horizontally rather than vertically. So our idea for area so far has been this same thing as we did for integrals in the first place, right? Take little rectangles that are horizontal, shrink that width to 0, take infinite many of those rectangles, and that gives you the area of the curve. Basically the idea of I want to take my graph here, and I'm going to add up a whole bunch of little strips vertically to get the area. Now that makes a lot of sense for the picture we have here. But for some regions, it might make more sense to think about this not as little vertical strips, but as little horizontal strips. So say instead I have a region that looks like this. Right, for this picture, doing vertical lines is kind of annoying, mainly because it's not vertically simple, right? There is a crossover point right down here where things are going to change. And also, in the region to the right of that point, it's kind of the same function on the top and the bottom. It's the same curve that's looped around in itself to give me the top and bottom there, so it might not be the easiest to handle. However, I can do this by looking at little horizontal lines instead. If I want to add up areas sort of in this direction, that's a lot easier to handle in this case. It looks weird because we're not doing the normal integrals like we did before, but this will be an integral in y instead of an integral in x. We're adding up rectangles vertically, so that's a dy change, as opposed to adding up rectangles horizontally, which is a dx change. Vertical rectangles, you tile them horizontally, that gives you a dx because your delta x is the change you get by stepping over to the right or left. In this case, with these horizontal lines, you'll have a delta y or a dy because your change here is a step in the vertical direction. And it's going to look strange at first doing dy integrals, but we'll see there's a lot of cases where this is really helpful when trying to sort out what's actually going on with a given problem. So in this case, this region is actually really nice because this is what's called a horizontally simple region, in that there is a single function on the right the entire time and a single function on the left the entire time. And that's going to make this one easier to do via a dy integral than a dx integral like we were doing for the rest of this section so far. So we say a region is horizontally simple if there's one curve on the left and one curve on the right the entire way. You want to think of this related to vertically simple, which was one on top, one on the bottom. And just like top and bottom are bounds in the y direction, right and left are bounds in the x direction. And so we're now thinking about this as bounds on x, integral in y, as opposed to before we had bounds on y, integrals in x. So if a region like this, if we let x equals g of y, right now we're thinking about x as a function of y be the right curve, and x of y be the left curve, we can find the area in a normal way like we did before, right? So we have a region like this. This would be our function x equals g of y. This will be x equals f of y, right? Keep in mind they're not going to be functions in the normal sense you've thought of functions by the vertical line test because they are functions of y, not functions of x. If you rotate this, then they're functions the other way. Then we can find the area by the same sort of logic we did before, but now we're taking little rectangles this way instead of the other way. So I just want to integrate the difference of these functions over this range. So it's going to be the area is the integral from, go with a to b again, of the x on the right minus x on the left dy, and the key thing to note here is because these are dy integrals, everything you write inside should be functions of y and be dependent on y, not x. This will be integral a to b g of y minus f of y dy. And we'll see an example in a bit of how you can think about these problems and how to make this work out. But things to realize is you can use this technique whenever you want to find areas of regions. If, for instance, you're given the boundaries as x equals f of y and g of y, it's probably easier to do it horizontally region than do it vertically. If it's a horizontal simple region anyway and you can solve out for x in terms of y, then you might as well think about doing this way as well. And regions where it's possible to visualize, where it's easier to visualize it as horizontally simple and just add it up that way as opposed to with vertical lines, you'll want to try this technique as well. And all of our techniques so far, multiple regions, curves crossing, area bounded between two curves, all still applies in the horizontally simple case or when you want to use y integrals, just like they did when you want to use x. So any of the techniques we learned before can all be applied to these sorts of problems as well. Here's the example we did before, but now I want to do it with y integrals instead of x integrals. So it's y equals 2x, y equals 5x, and y equals negative x plus 12. I'll draw the picture here again. And again, we're finding this region here in the middle. And last time we found the intersection points, so I'll just write those down here again. Now, since I want to do this with integrals in y, I want to picture drawing horizontal slices and those tiling up over my region. So I'll have slices like this that I'm going to add up with dy integrals. So again, this region is not horizontally simple either, but I can break into two pieces that are by drawing a line across here at y equals 8. So we're going to have two separate regions here and have two separate integrals. So the area we can find by the following. The first is the bottom region, which in terms of y bounds, right, we're doing dy integrals. Everything has to be in terms of y and have y bounds on the integrals. Goes from y equals 0 to y equals 8. I will need the x right, which is the green function, minus the x left, which is the orange function here, dy, plus the second one, which will be the same picture from y equals 8 to y equals 10. The right side is the purple function, and the left side is the orange again. Now, to figure all of these out, when I have to plug in, I need to solve out for x in terms of y in each of these functions. So let's go back up and do that. For the purple here, I can solve out for x by adding x and subtracting y from both sides. So x is 12 minus y. For the green, I get that x is y over 2. And then for the orange, I get that x equals y over 5. So now I can plug all of those into my expressions and then solve out the problem just like I had done before. So my area should be the integral from 0 to 8. For blue, we had y over 2 minus the orange, which was y over 5, plus integral from 8 to 10. This one, which was 12 minus y over 5 again. And now we're just going to solve this out. This becomes 3/10 y plus an integral from 8 to 10 of 12 minus 6y over 5. We can then find antiderivatives. 3y squared over 20 from 0 to 8 plus 12y minus 3y squared over 5 from 8 to 10. We can plug in our endpoints, which gives us that, and then we can start simplifying things out. Simplify some fractions, cancel out some terms. The two denominators with 5 come to a 240 over 5, plus that gives me a 60 minus a 96. 240 over 5 is 48, and this comes out to 12, just like it should. So the main idea you want to think about there is it didn't matter which way I solved the problem. I got the same answer either way. It just depends on how you want to picture, how you want to think about these problems, what the best way to attack them is. It'll work either way. Whichever one you see and whichever one looks easier is the way you should go at when trying to solve problems like this.